of your face in that slightly undignified posture that so many of us seem to have adopted. And the things around you, the walls, the furniture, the device you're looking at, those things are simply there. They are in definite places. They have definite colors, definite shapes. They have a solidity to them, a there-ness, that we take as the most basic, inescapable fact of existence. Things are what they are. Things are where they are. And crucially, they remain what they are and where they are, whether or not you happen to be looking at them. When you close your eyes, the room doesn't dissolve. When you leave the building continues to exist. The world does not need you in order to be real. This is the picture of reality that every one of us carries around, all day, every day, so deeply embedded in our experience that it doesn't even feel like an assumption. It feels like the ground beneath our feet. It feels like the most obvious, most unchallengeable thing in the world. I am going to spend the next hour, well, supposedly an hour, knowing my tendency to get distracted by interesting side roads, I'm going to spend this time systematically showing you why this picture, comfortable and familiar as it is, appears to be wrong. Not approximately wrong, or wrong in some peripheral, technical, doesn't really matter sense. Wrong in its foundations. Wrong at the level of what the world is made of and how it behaves when no one is looking. And I am going to show you this not with philosophy, though there will be some of that, and not with speculation, though there will be some of that too, but with data, with experiments, with results coming out of quantum computing laboratories right now in 2024 and 2025 that are, if you understand what they mean, rather deeply unsettling. I have been thinking about these matters for a very long time. I was a young man when I first encountered quantum mechanics, properly, not the equations, mind you. The equations come relatively quickly, but the meaning, the interpretation, what it is actually saying about the physical world. And I remember the sensation, sitting in a lecture theatre in London, of the floor shifting slightly beneath my intellectual feet, of realizing that the theory I was being taught, the most precisely confirmed, most experimentally successful theory in the history of physics, was describing a world that bore very little resemblance to the world I thought I lived in. I have never entirely recovered from that sensation. I am not sure one should. So, let me begin at the beginning. Let me begin with what quantum mechanics actually says. A particle, let's say an electron, though it could be a photon or an atom, or in principle any physical object, a particle, according to quantum mechanics, does not have a definite position. Not in the sense of we don't know where it is. That would be ordinary classical ignorance, the kind of ignorance you have about the position of a coin spinning in the air before it lands. Classical ignorance is simply about missing information. Given enough information, you could, in principle, predict exactly where the coin will land, because the coin's position is already determined. You just don't know it. Classical ignorance is epistemic. It is about knowledge. Quantum mechanical uncertainty is something different, something stranger, deeper. The electron, before measurement, does not have a definite position, full stop. It is in what we call a superposition of positions. It exists in a perfectly precise mathematical sense, spread out, delocalized, over a region of space, described not by a single point, but by a wave function, which is a complex valued function that assigns to every point in space an amplitude, the square of whose magnitude gives the probability of finding the electron there if you choose to look. The electron is not secretly at one definite location, waiting to be discovered. It is genuinely, irreducibly, non-locally present across all of those possibilities simultaneously. And the same is true of For measurement, these things are in general indefinite. They are in superpositions. And this is not ignorance. This is not an artifact of an inadequate theory that we expect to improve. This is what quantum mechanics says at its core. Quantum mechanics is correct. Extravagantly, embarrassingly correct. The predictions it makes have been confirmed to 10 or 11 decimal places. There is no other theory in science with that record. Now, you look, you measure the electron's position, something happens. The wave function, which had been happily spreading out and interfering with itself in its ghostly quantum way, the wave function changes. It collapses, or appears to collapse, onto a definite value. The electron is found here, not there, here, one single definite result. And after the measurement, the electron behaves as though it always was here, as though all those other possibilities, all those other positions encoded in the wave function were never real at all. This process, what we call wave function collapse, or the measurement problem, is the deepest, most unresolved, most philosophically vertiginous problem in all of physics. Not the dark energy problem, interesting as that is. Not the reconciliation of quantum mechanics with general relativity, urgent as that certainly is. The measurement problem. We have had quantum mechanics for 100 years. We have used it to design transistors and lasers and MRI machines and atomic clocks and GPS satellites. The entire technological infrastructure of modern civilization is built on quantum mechanics. And yet we do not know what it means. We do not know what happens physically when a measurement is made. We do not know whether the wave function is a real physical thing or merely a calculational tool. We do not know why the collapse occurs. We do not even know, in any satisfactory, rigorous sense, what constitutes a measurement in the first place. This is the honest situation in physics. And anyone who tells you it is resolved that we have simply to pick an interpretation, Copenhagen or many worlds or Bohmian mechanics, and the problem goes away, is, I'm afraid, mistaken. The interpretations shift the problem around. They resolve some aspects and create new puzzles elsewhere. The measurement problem remains open. Now, you might say, why does this matter? The theory works, the predictions are right. Why should we worry about what's happening behind the equation? This position, sometimes called shut up and calculate, a phrase usually attributed to David Mermin, though he has disputed that attribution. This position has dominated physics for much of the past 70 years. And I understand why. In the day-to-day business of doing physics, you do not need an interpretation. You calculate, you compare to experiment, you are satisfied, but I think this pragmatic quietism comes at an enormous cost, because the question of what quantum mechanics means, what it is telling us about the nature of physical reality, is not merely philosophical decoration. It turns out to matter enormously for the deepest questions in science: the nature of consciousness, the origins of the universe, the relationship between mathematics and physical existence. These questions require an answer to the measurement problem. And the quantum computers are now forcing the issue. Let me explain what a quantum computer is properly, because there is an enormous amount of confusion, and I think it's fair to say a certain amount of deliberate obfuscation in how these devices are described in popular media. An ordinary